Hello and welcome to another episode of the Building Sciology Potty. This weekend just gone was the International Passive House Open Day weekend, so I really hope that you got along to see and feel a certified passive house for yourself. I'm absolutely thrilled today to have the founder of the International Passive House Institute himself on the show, Dr. Wolfgang Feist. It was super lucky that I got to record this interview with him just in time to release today, so I really hope that you enjoy our conversation. Before we get started, though, I just want to say I would love it if you could hit follow on your chosen podcast listening platform so that you don't miss a future episode. And if you are loving the content, please leave me a 5-star review because that helps push the show out and helps more people discover the Building Sciology Potty. All right, let's get into my discussion with Dr. Wolfgang Feist. Cheers. Hello and welcome to the Building Sciology Potty, where we talk about better buildings to live and breathe in. My name is Jess Kismet and I am your host. When we talk about truly revolutionary shifts in building science, very few ideas have reshaped the way we think about comfort, energy, and durability like the Passive House standard. Behind that revolution is one man, Dr. Wolfgang Feist, physicist, researcher, and founder of the Passive House Institute in Darmstadt, Germany. Long before net zero and sustainability were industry buzzwords, Wolfgang and his team were building airtight, ultra-efficient homes that changed what it feels like to live in a building that truly works. Today, I am honoured and honestly pretty excited to dive into this conversation with the man who started it all. Welcome, Dr. Wolfgang Feist.
Thank you. Thank you for the invitation. I enjoy to be with you.
Excellent. All right, so let's dive into the first question. I would really love to know why you started the Passive House standard in the first place. Why did you create it? Take us back to the mid-90s or even a bit earlier than that. And I'd love a little bit of a history lesson.
Okay, I'll take you much earlier. In 1897, Fridtjof Nansen in farthest north, he wrote the following thing, I cite. The sides of a ship were lined with tarred felt. Then came a space with cork padding, next the deal paneling, then a thick layer of felt, next airtight linoleum. The skylight was protected by 3 panes of glass. The front is a comfortable abode. Whether the thermometer stands at 22 degrees above zero or 22 degrees below it, we have no fire in the stove. I'm thinking to having the stove removed altogether. It's only in the way. End of citation. So, well, that sounds a lot like passive house. Well, it's a passive ship. So
I started in a ship.
With physical solutions for a comfortable home, be it a ship, were already known by experienced engineers at the end of the 19th century.
Yeah.
It's interesting, huh? Well, at the
very.
time where we started the new research on the passive house in 1987, we didn't know about the front. We discovered that later. But what we did know, that was the experience from Sweden and Denmark with the so-called low energy buildings. We already had decades of experience with low energy buildings. And I visited Lund University beginning in 1986 to learn about that Swedish research. I wanted to use these results for the development in Central Europe. And I was guided by Professor Bo Adamson. And he was somehow the foreign minister of building physics of Sweden. He was traveling around the world. And he had just been to China to give advice to the local Chinese government how to improve the thermal comfort in residential buildings in southern China. And the delicate fact was that heating was forbidden there. So they couldn't run a stove. And quite often that was not really comfortable. The temperatures
I can imagine it was pretty cold.
12 degrees, sometimes.
Oh my gosh, yeah.
See, near to Shanghai, and less. And now the government asks, how can we improve the thermal comfort in these buildings without introducing active heating? Because we still had a lack of fuel. So Adamson ran thousands of computer simulations to look into the least expensive measures to improve that comfort. And he called these homes passive houses. That is where the name comes from. Because from a technical viewpoint, if you run simulations on buildings, uh, it, these are thermodynamic simulations, but the structure of the mathematical equations, they are the same as the structure of electric circuits simulations. So there are resistances and heat capacitors and so on. And in electronics, we call systems which do not introduce energy passive systems. So that was where the name came from. So
Yeah,
when he
cool.
came back to Lund, to the university, and he met me, and he had a fixed idea. That is, what about constructing passive houses in the much colder European climate? That is what he came back from China. And my first reaction was, now my friend has gone insane. And from my own reaction is why I understand, but something like that is quite often the first reaction to such an idea. I've seen that almost everywhere. You come back to that later, I think. But after a few days of discussion, we came to a conclusion. Yes, why not? Let's try it. Physics doesn't stand in the way. It might be a bit challenging with the contemporary state of art and construction that we were aware of, but it should be possible. And now it was up to me to start not thousands, but 10,000s of simulations of the thermal behavior of such buildings within Central European and Swedish climates. And we wanted to find how this could be done. But it didn't stop with the theory. It had to be built. So we had to develop highly insulating building envelopes, really airtight and without important thermal bridges. We had to look for triple pane, double low emissivity window panes, insulated frames, energy efficient ventilation systems. A lot of things that had to be developed and produced in small pilot series. But was done in 1988 to 1990, mainly in that time. And the building was constructed in 1991 to 1990, end of 1991, to just one day to one year to realize the building. It was built by a local construction firm. And it has been occupied by 4 families since then. So that is how it started. Well, the story goes on. It could fill several hours. How it was monitored. They have some 200 sensors. Not so surprising nowadays, but in 1990, we compared the theory, the simulation, with the measured results. And already the very first passive house, it wasn't that expensive. Well, it was expensive enough not to be copied just one to one by everybody from the very beginning. But it wasn't even thought this way. It was thought as a proof of concept, scientific proof of concept, and a leading idea how the environment could be improved. That was so that was the starting point. And it took several more steps to realize, well, this isn't only a scientific research. It could really be done in practice, and it could be done not only for Central European climates, but I think almost everywhere on the planet. So there are several other parts of stories. There have been lots of contributions from all around the world. One time we had a visit by, I don't know whether you know him, by Amory Lovins from the Rocky Mountains Institute from the US. And he was the one who said, oh, well, Wolfgang, you are completely wrong. I was shocked. So, well, what he was somehow the Pope of energy efficient construction. And
Yeah.
now you are completely wrong. No, he said, no, this is not just a scientific experiment. This was what I tried to tell him. He said, this is the solution. So now just start to get it less expensive, to develop the components we can produce in factory-sized, small, medium, and even big construction and manufacturer scale. Huh? So that's another part of the story. Yeah? So there are a lot of contributions like that. And some of them, you know, from the development in Australia or in other parts of the world. Yeah. So this is how it came to be.
Fantastic. Thank you. So was it 1891 you said? Yes.
The book is from 1877, and
Yeah.
from, I don't know when the from was built. It was even earlier. He used that to travel around the Arctic cycle. Yeah? So he was months away from home, and he really described why he did it the way he did, because he had already some experience what happens if you have a boat or a home or whatever you call it, and you take it far to the north where it's extremely cold, and then you have people inside it. Yeah, he knows about. He did know. He writes about it. He know that the water was running down the cold surfaces. The beds were wet, and after a few weeks, it wasn't possible to sleep any longer. And so he came to the conclusion if he wants to be successful to reach the Arctic cycle and to travel with the Arctic ice, he had to build a ship which can withstand these conditions. This is how he, from a scientific approach, he designed the from. And if you look into, I cited his text, if you look into that text, you see the solution was a passive ship.
That's
Already in,
fascinating.
well, I don't exactly know when he built it. It must have been in 1870 or something like that. Yeah.
Mhm.
So quite early. Yeah.
That's fascinating. And so the building in Germany, your very first certified passive house in Darmstadt, you said that you monitored that building. Did it perform how you thought it was going to?
Well, it was one of the other surprising things. It performed better than our calculations had always been on the safe side. Yeah? Because of course it would have been quite a risk. This was not a experimental building, just with simulated occupants like a incandescent bulb or something to heat it. It was really occupied building, and the families who moved in, they paid for that building. We didn't even have a huge research fund. Not at all. It was just
So it was for
financed
private.
by
It
the
was for
people
private
moving
owners.
in. So a private, yeah. So
Yeah.
we had to make sure that it was really working. So we calculated on the safe side, and we also looked for all the details. Just to mention one thing, uh, there hasn't been any really airtight envelope being built, I think, all around the world at that time. And we knew about the experience in Sweden. The Swedish had at that time, we had a standard going for 1.5 air changes per hour, and we thought, well, maybe we can meet zero 0.8, something like that. And we took it very seriously. We looked at every detail we built. I even was going through building and painting every part with a of course, with a diffusion open paint.
Of
Things that
course.
building physics knew at that time
Yes.
already. Yeah. So, but airtight. Yeah. So, and then the first pressurization test came. That's another story. Yeah. Because pressurization test at that in that period, that wasn't available as a standard measurement. It was something that had been tested in Swedish laboratories. So we had to build our own equipment to do that test. Yeah, and then slowly the ventilator went on, and then we already saw. Oh well, suddenly the pressure built up. Only with very small movement of the ventilator. And so we know, okay, yeah, that seemed to have worked.
Yeah.
What was the result? It was a 0.17 air change per hour in 50 result. The very first.
Your very first go.
So this is where we say, oh no, now we see it's not that difficult as a lot of people think. And it's also one thing I have to tell you about that air tightness. That's often some people fear it might be tight or whatever. Yeah. So this isn't very tight. Yeah? What is tight is a spacecraft. A spacecraft is tight. It's really airtight, and it's good so because it will lose. If a spacecraft would only be as tight as our passive house is, 0.2 air changes per hour, it would take 10 seconds and all the air would be gone from the spacecraft. The pressure,
it's not good up in space.
From inside out. So air tightness might even be the wrong word to be used, because from a physics point of view, this is not tight. It's just a little bit tighter than ordinary. So you don't have the drafts, you don't have the wind infiltration, you don't have all the humid airflow out through the envelope, which will at the end destroy the envelope. Yeah, this is what we avoid, but it's still not tight in that sense. Huh? It's
terminology matters, and that term does scare people. They think they're not going to be able to breathe.
Yeah, and that's not true, and that's also one reason you maybe come back to that. It's one reason why I even do not recommend to go much further when we reach with a good passive house envelope. That's in the range of 0.2 or 0.3 air changes per hour with 50 Pascal pressure difference, because that is really good enough. It's good enough that the passive houses will work and that there will be no damage to the envelope, and that it will work for hundreds of years without condensation. Yeah, this is good. So, and now if there is a situation where the ventilation system shouldn't work, it can happen. It's a technical system. You can have outages of electricity and whatever. It can happen. But it still doesn't matter, because if it's a 0.2 or 0.3 air changes with 50 Pascal, you still have enough air to survive. It's no problem. So nothing will happen. No, it will be a little bit smelly after 2 days, something like that. So
a little bit stuffy.
So you will realize, oh, there's something not working, and you might open a window or whatever. Yeah, still you can still do that in a passive house. There's no danger with that, not at all.
And I have to ask, where did the 0.6 air changes per hour standard come from?
Where did it come
we
from?
We all want to know.
When you start to design, and you start to realize what are the reasons why normal building envelopes are so untight, so leaky, you see that you will end in a range of 0.2 to 0.3 air changes per hour with 50 Pascal. This is what we realized with the very first project, and what we also have seen with every experienced builder. Yeah, when they do the first project, they complain that it's too difficult and all these things. But after 2 or 3 realized constructions, we come to the same point. If you really design it to be airtight and be a little bit conscious about what you are doing on the building side, you will reach 0.2 or 0.3 air changes per hour. So, but I see it's for a very first try, it might be a bit challenging. So I was looking what might be a good compromise. So what we need, it should not be at all higher than 1, because after 1 there might be structural damage by exfiltrating humid air. Yeah, and also somewhat oily, but we can also avoid it by looking at the pressurization test. So if you do a pressurization test, you will find the leaks and you can repair them. And so, well, now we could have discussed whether it should be 0.3 or 0.4 or 0.5 or whatever. And well, higher than 0.6, it just hurts. Yeah, because it's so easy to do better. Yeah. So yes, there is science behind it. Should be
Yep.
as airtight as possible, and
Yep.
it shouldn't be really spacecraft tight. Not
Yes.
necessary. Yeah. So
Yep.
somewhere there are the solutions, and 0.6 is quite a good compromise.
Okay. So you were expecting 0.2 or 0.3, and 0.6 is like a little bit of like a buffer.
Yeah, the 0.6 is something that, well, if we install triple glazed windows, for example, and on the other side only still have leaks in the frame, which add up to more than 0.6 or something. That's not there's something wrong.
Yeah. I think that's probably
Yeah.
one of the bigger problems we have in Australia is the glazing components. They're definitely the biggest source of air leakage in our certified passive houses. So,
But
looking
it's
forward to
so
some
easy.
improvements in those.
Yeah, it's so easy to fix. Yeah? And this is
Yeah.
it's just a question of know-how and with the winners. This is just to explain another thing. This is why we came up with component certification, because we know how you can improve that. It's not difficult, not difficult at all. We have millions of examples of manufacturers' windows which are really tight. Huh? And so yes, this is possible. It's not only possible, it's affordable. It's one of the easy points. But some people who start with their first projects, they might think, because they are not used to it, which is always, well, I'm a math teacher, and so I know it's sometimes difficult for a young person to understand what the general concept of, say, a differential equation is. Yeah, but it's only because it's new for them, and so if you learn about it, if you understand it, if you see what's going on, it becomes easy. And
Yeah.
that's the same here. Yeah. And
100%.
this is somehow also the secret behind the development, because this is what is what has happened everywhere. Yeah. When people started building passive houses in a different place, say, for example, Romania. I well remember the first discussions we had. Oh, that airtightness, it's impossible. We can't do that in Romania. Yeah? And they started and did first projects and ended with 1 or 1.1. And I said, well, it's still quite good. But you will see, after 3 years, you will be proud to pronounce, oh, we reached 0.1 or whatever. Yeah? Always happens. Yeah. Always
It
the
does.
same.
It becomes a competition. It becomes like even between building companies and between supervisors, they just want to beat each other.
Yes, but also let's be honest here. It doesn't matter whether it's 0.3 or 0.1. It's not
Yeah.
a big difference. Yeah. So
Yeah.
this is why I also say, well, it's the passive house is somehow a sweet point where you this is what you need to have a reliable performance. Yeah.
Hmm.
Without
Hmm.
any interference of whatever strange effects high wind velocities or whatever would be. Yeah? It
Hmm.
it's working. Yeah. So
Hmm.
and we don't need more than just that.
Hmm. And the point you make is obviously very valid. It's easy when you know how. It's easier when you know how, and you just have to stay curious and just start trying
You see,
to do a little bit better.
we were successful with just the theory in the background, no practical experience with very
Mm,
first project. Yeah, just the theory,
mm,
the physics behind it. How can it be that there is an airflow of inside out through an envelope? Oh, well, that's a relatively easy question, and from that theory we derive how how you have to do it. But there's something more about it. It should also be keeping that air tightness for say 40 years, 80 years, 100 years. Yeah,
mm. Have you tested your first passive house since it was first tested to see if it's still holding up?
of course.
Yeah,
Of course,
and is
well,
it?
the last big test was just a few years ago, and within the measurement accuracy, it didn't change at all. Yeah. So this is not something which is automatically true. It's
Mm,
true if the concept you are using is designed for longevity.
hmm
And, and this is what is also one of the background. This is what we always wanted from the very beginning. Yes, a building can work for hundreds of years. It's not a This is not a big problem. It can be done. We have done it in the past, and we can do it now.
My next question is around the 5 pillars of a passive house. And over in Australia, and I guess globally, but there's a discussion here about passive house principles in inverted commas. And there are technically there's no such thing as passive house principles because it's a certified standard, not a set of guidelines. So the 5 core areas that you have identified, the 5 pillars of a passive house: air tightness, thermal bridge free, continuous insulation, energy efficient mechanical heat recovery ventilation, and high performance windows. They are now widely recognized as the foundations of a good building performance. So, how do you feel about the industry using the term passive house principles without certification?
See, that is a progress. Yeah? The narrative
hmm
changed from this is impossible. Yeah? Then came this is one-sided and exaggerated. Yeah? Then came it's too expensive. And now we have, well, we already do passive house principles.
yeah.
Well, really?
So you don't
Do you?
mind?
No, well, my question is, well, really, do you? Yeah. So, uh,
Do I mind?
so as long, no, these people saying we already do passive house principles. We have also had that in Germany. Yeah? And my question is, well, really, do you? Because as long as the building doesn't meet the performance-based standard, it's not a passive house. No? And a good analog for that is a symphony. You can have first-class violinists, clarinetists, and so on, but as long as all these people aren't working together in a well-trained orchestra, the result might still be a cacophony.
hmm
So that is why there is more to a building than just using one or another component. Yeah? It's how it really works together, and that is what is behind the passive house concept. And this is where the certification is really helpful. This is how it's meant. It's meant to be helpful because it's not. Of course, you do not need a certification. It's you can do it if you want, and I can only highly recommend that. I have seen a nice paper on that by Kara Rosemeyer. You might know her from New
Yes,
Zealand.
Aneka.
She was talking about that, and she showed what is why this is such a big advantage because the certification process is a transparent process. It's something like, well, if you go to industry, in industry, they are improving the way they manufacture goods step by step, by looking into results they have. But it's somehow secret to the manufacturer what we do. So now here we have an open and transparent process, learning from each project which is being done, and implementing the know-how gained by this project into the process. So this is a really big advantage to use that know-how.
Hmm.
It's not about controlling somebody. It's to assist people to be successful in what they do.
Hmm.
This is
Hmm.
how I think about it.
Yeah. So you don't see a particular problem with using the word passive house principles as long as people are learning and improving.
Yes, what is really important that not me and not other people working in the field want to be responsible for things which do not use the state-of-the-art check and balance, which is necessary to make sure that it's working. Yeah? So that is something in the background. So it doesn't help if you say you are building the passive house principles, and at the end you have mold in the building.
Mm,
Yeah, and it also doesn't help us. Yeah, to have such a situation. So we have to be clear about that. Um, if you claim to have a passive house, I always ask, is it certified? No,
Well, that's a different thing. Yeah. Claiming to have a passive house that's not certified, that's not
it's
integrous.
danger, and I have seen that. This is one of the reasons why we offer
Yeah.
that process. Yeah, I have seen that in Germany when they started low energy buildings without quality control. There have been so many dangerous building problems with humidity and so on.
Hmm.
So that at the end, the narrative was, "Oh, don't do that. It will destroy the building and so on." And now I'm a physicist. I know no, that's not true. On the contrary, if you do it in a proper way, it will improve the longevity of a building. It will
Hmm.
improve indoor air quality. We all know that from the experience. Yeah. So the question is, how can we make sure that it's really working? And that is where we try to assist people with.
Hmm.
Yeah.
Mm. Yeah, we have builders in Australia who, and a lot of homeowners or people who are building houses, who they have this, perception that passive house, like you mentioned earlier, is too scary and air tightness is too hard and it's too expensive, and so they say we want to build to passive house principles, and what they mean is they want just a slightly better building envelope than what the minimum construction code requires here, and I think that's a good thing, but there is the inherent risk that you're going to create a problem.
Well, I think the risk isn't that high, but there is a risk, and and uh, the the passive house standard is a way to avoid that completely, because all that experience is always taking and it's a ever improving process. No? So this is why it's working so well. And this is why you also see we have not have it's nearly impossible to believe that we have not have any problem with mold or something like that in a certified passive house. It's now 20 years and it's hundreds of thousands of buildings. It's almost unbelievable.
Yeah,
Yeah.
that's
This is
incredible.
rolling, and this is not something which uh, it's not produced in just one factory like a Mercedes or whatever, and even they don't have a almost zero failure rate. Yeah, even they don't have. But this is done by ordinary architects, built by ordinary construction firms, built with components, well, improved components, which are also very much improved to ordinary ones. But and this is still working because it's so well met what you really need to have a successful building.
It's time for a quick sponsor shout out. Today's episode of the Building Sciology Potty is proudly brought to you by our amazing sponsors, Enduro Builders and Climasure. A huge thank you to these incredible businesses for supporting the podcast and helping us spread the word about better buildings to live and breathe in. Your support makes this podcast possible. Please head over to their websites and follow their social pages.
Yeah, it's that is an incredible track record.
I think so, but this is not you see, this is not our idea or our achievement. It's all these people who engage in that, and I can see that. I can see it everywhere. When you start to look into the details, and if you understand the building physics behind it, you will of course come to the same conclusions. As we did. So it's a self-accelerating process, what's happening here.
Are there any changes coming to the Passive House standard? This is a bit off script, but are there any changes coming, any developments or any changes in the future, or is it going to stay as it is? To
be honest, I was surprised how little the changes have been so far. Yeah. So what we do and recommend now, it's all not very far from what we have done in the very first experimental building. It's surprising, yeah. For me as a physicist, it's surprising. But of course, there is progress all the time going on. The energy recovery rates of the HRV system. So I don't know what it's called in Australia, maybe.
HRV.
Mechanical ventilation with heat recovery or whatever. They call it in different ways. These things have been improved. When we started, it was very difficult to have a system which has at least 80% recovery rate. Nowadays, you can buy systems with 80%, with 90% recovery rate. And now that sounds as if that's only a little progress. No, not at all. Because with 80%, you have still 20% losses. And with 90%, the losses are reduced to 10%. And that means that's half of it. Yeah. So it's much easier now to build a passive house than it has been when all these components were not available. The same thing happening with windows. So there are now the production of really vacuum glazing is starting all around the world. And it's also much better than what we had in the past. So it also makes it easier to build really energy efficient buildings. So there are all these changes we see. Yeah? There's also always discussion about other things like, say, nowadays, big discussion about embodied carbon. That's another thing could be discussed for a long time. Yeah. Just to see how a scientist like me approaches this. That is, there is a something that most of these discussions do not look into. That is the lifespan of a building. A building is not a Coke bottle, which X and hop. You have the material, you have the aluminum, you use it for 5 minutes, and then you throw it away. Yeah, this is embodied carbon. Yes, it is. Yeah, but a building, a good building will be there for how long? 80 years, 100 years,
Fully, a long
200
time.
years. Yeah. Even longer. And this is what we'll have to optimize. Yeah. And then if you look into that, it's a whole different story.
But no changes to the framework itself, but there's upgrades. There's always component upgrades or component improvements and industry improvements all the time.
No revolutionary. I wouldn't see any revolutionary development in the next few years. But you can't be wrong. Yeah, it's not the future. It's not easy to predict the future. Yeah, I would have thought when we started the whole thing in 1990, I would have thought that say a couple of years later, 10 years later, there will be completely new ideas, and it would be a very different ways to go on. And I'm a little bit surprised that it's still all mostly the same.
Mm.
But I'm also not surprised as a physicist, because it's so clear to understand. As long as you
Yeah.
have high losses from a building envelope, and you have to substitute for these losses by a big amount of oil or gas or coal, you have a problem. Yeah? And so the very first step is to reduce these losses. Yeah, easy.
Yep. Yep. The overarching purpose remains regardless, and the science stays the same. The physics
It
stays the
becomes
same.
easier. It becomes
Mm.
easier from year to year, because more components are going to be available. It's would be easier to install. This is where we are concentrated on at the moment, to make it even less, to use less effort to reach at the same good results. Yeah.
Mm-hmm.
This is possible. This has been done in technological development, in all kinds of systems, and it's possible in buildings as well. And we have seen that. Yeah, that's the reason why. Well, just to be honest, the first passive house was not a single family home.
Mm.
Two reasons for that. First reason is it wouldn't have proven anything, because the behavior of the occupants has such a high influence on what's going on in the building, that just having one example doesn't work. But that's only one reason. The other reason, it would have been really difficult to build in the cold Central European climate a single family passive house in 1990. Yeah, because we needed the 30 centimeters of insulation. We needed the thick extra insulation of window frame. We needed the preheating of the air by earth buried tubes. Yeah,
Yeah.
all things which you now don't find in new passive houses, because all the components have become even better than they have been for this research project. And now you can build single family passive houses near the Arctic Circle. No problem. It's always done. Yeah. So which is what is progress, and
Yeah.
the technological progress is much faster than I have anticipated, but it was also much less revolutionary. Yeah, it's the same concepts being improved, and we are getting better and better using these principles.
Brilliant. So, talking about building a passive house in Antarctica, there's often, we often hear that passive house is not a standard that we need in Australia. It's designed for Germany, where it snows and, all the really cold climates. What is your response to that?
Let's say, when we started these first examples, 1990, in our region, yeah, most peers, even the peers in building industry, they called it too hard, too Swedish, not needed in Central European climates. Does it sound familiar? Yeah.
Even you guys.
Come on. Building physics works the same, whether it's in Australia or in Canada or in Hong Kong.
And that's the end of the story, people. That's it. No further discussion needed.
Exactly.
So
and
stop
also,
it.
and also the human body. Yeah, we are one species. Which is very interesting, also from the formal comfort aspect. That was research that was done by the colleague Ole Fanger in the early 60s. Yeah, and he looked into what is it? Why do we feel comfortable? Yeah, and he has done a lot of experiments to look into that, and he came up with a theory of thermal comfort. And it's working. And the surprising thing is that it's the same for all human beings. It's not different. Yeah, whether you are in a white, a a person of color, whether you are male or female, even the sick react the same way. Yeah, only very few people with very complicated disorders might have other experiences here, but 99.9% of people, it's the same genes, it's the same
Some husbands
reaction.
and wives might disagree with you with that thermal comfort issue.
There's another aspect to that. That is, if you want to keep peace, it's also important to know this is one species. Yeah? There's no,
Yeah.
there are no big differences. Yeah, and to the good and to the bad. Yeah, it's
Okay. Excellent. Well, I hope that puts that one to bed.
well, it never does. It never does.
No,
And also,
we can try.
it's sometimes which is a fun discussion. Yeah, you
Yeah.
can talk about that all day long. Yeah, clear.
Yeah.
So what's necessary is you do it. It's not you don't only talk about these things. It's interesting. You can talk about it, but you just do it. And when you experience what's going on, and when you see, yeah, which is working. Yeah, that works.
Some people joke that Passive House is like a cult. There's a perception that followers can be a bit one-eyed, and there can be quite a strong emotional reaction to this standard either way, either for or against. Why do you think that this building standard inspires such a response? And do you see that as a strength or a barrier?
Well, let me come with something completely different. That is, when Albert Einstein, when he presented the theory of relativity, that aroused strong emotions, even in the scientific community. Yeah? Some even called it Jewish physics. Yeah, remember back, that was a very very dangerous time. No? But others were thrilled. They realized that this solved one of the biggest problems of physics at that time. Yeah? So it is nothing which is special for any innovation anywhere. And let's also be honest, Passive House isn't such a big innovation. It's still a building. It still has roofs, windows, walls. Yeah, it's not.
You're not reinventing the wheel.
No, it's not. It's not reinventing the wheel. Yeah? So now, on the other side, I'm a scientist, and we scientists have to be critical. And being critical, that means being self-critical. This is something nowadays also is a big misunderstanding that say we are critical. We just criticize everybody else. No, critical means you have to be self-critical. Yeah? Socrates once said, "I know that I do not know." And we nowadays, we have to recognize that by large, that is still true today. Yeah? We don't know much. We have learned a great deal, and we are on the way to learning even more. And I quote Barack Obama now here, that is, he says, yes, we can. Yeah, we can learn these things. And well, now, not everybody enjoys that debate. Yeah, and when you look into some of the critics, they are just backwards oriented. Yeah, they just want to have the world back like it was in the 1800s or whatever. No? However, of the course of the development, I have witnessed on several occasions that those who initially resisted to such innovations, they later made extensive use of the research findings. And some of them even contributed with their own projects. So I'm not criticizing the critics. Yeah? We can learn. We invite them to learn. Yeah, and what we need
absolutely
is that way of interactive discussion. Yeah, this is very creative, and this is a way to make progress. Yeah?
Yeah, I think it's just about staying curious and asking questions and continuing to learn. And there can certainly be a bit of a fixed mindset amongst some people, and they like to keep things the way that they know and understand, and I get that. But I think,
Change is sometimes hard, yeah. Sometimes to
yeah,
realize that you
ag-
can do things in another way. It's
yeah,
sometimes hard. We have to
yeah,
understand. You see, when I introduced when the first idea came up with Bo Adamson, and he said, "Let's build passive houses in Central Europe." My idea was he's gone insane. Yeah,
yeah.
so so I can understand that, but that doesn't mean that you don't have to try. Yeah, you
Mm.
try.
hmm So curious. And I think that leads on segues quite nicely into my next question, because you have said before that the building industry resists change not because of science but because of habit.
Mm.
And for our listeners, whether they're builders, designers, architects, or homeowners, what do you think is the most effective way to challenge those habits or fix mindsets, and fear of something new and different, and also of cost? What do you think the best way is to kind of start to shift that?
Now, energy efficient construction nowadays, it's now not longer just theory. Yeah, that has changed dramatically since the 1990s. When we built the first house, there was no example. Yeah, but now there are thousands of built and occupied examples. I was impressed by the number of projects which were presented by the Australian Passive House Association, yeah, already existing in Australia. So therefore, what I recommend is the first step is to visit an existing house. See it with your own eyes, yeah.
Yeah.
Feel the comfort, smell the air, talk to the residents. Yeah, it's so easy. The open days of a passive house are coming up right now.
Yeah, it is actually in a few weeks, couple of weeks.
You can do that, yeah.
Yeah. Well,
No,
we've the company I work for has a certified passive house, and we're opening it up. So
fine, yeah. Good to see.
yeah,
This is it's the very first step, and this is important. This is what I have learned. It is something like also now again coming back to the math teacher part. Yeah, if you teach math only in an abstract way, I realize why people resist to that. Yeah, it's not you don't get the feeling, you don't see what it's good for. Yeah. But you can implement it in your daily life. You can understand where you can use it for. And this is why this visit in an existing passive house is so important. Yeah, you can see this is not something abstract. It's something really concrete. Yeah,
and
and
achievable.
and achievable because it's there. And
It's being done.
you can talk to those who are residents there, and you can talk to those who have built it and those who designed it. Yeah. And
Yeah.
then next step is there are established training courses for builders and planners. Yeah. And that's a globally standardized educational concept. Yeah. Designed to qualify all the participants so they can plan and build their own projects. It's something you can do. This is very interesting. It's not something you have to buy. It's something you can do.
Yeah.
Interesting. That's an interesting concept, right?
That is actually. You can
not a
actually be
project.
part of it. Yeah.
Yeah, you can be part of it.
The creative process.
And it's also I think we should start to think about other parts of our economy, other parts of our industry, to think about whether there are also things that we can where we can contribute. Yeah, that it's not only done just by some authority which tells you how to do, but to gain your own experience and to learn about it. Now, building material manufacturers, what can they do? They can study the criteria for their specific components to make them suitable for passive house. And then they might contact some peers or the Passive House Institute directly, and the scientists and the engineers where they are happy to assist in development of these improvements. And that's similar to the air tightness thing. This is once you learned it, once you did it once, you will see it's not that not that that big an effort. It's not that difficult to do. No? This is what you can learn.
I think the biggest thing that Australians struggle with is the fitting a certified passive house into their budget,
Oh, look, I see.
because they
Mhm.
perhaps prioritize things that aren't related to the performance of the building.
Yeah.
So all they need to do, the simplest way to fit a passive house into your budget is just to make the house a little bit smaller. And that is a bit of a shift for a lot of people that they don't really want to make their houses smaller. Because they want the dream. Um, but yeah, it's very achievable on most budgets that people have got to build a house with these days. There's just has to be some. You have to work with what you've got.
Let me a bit even more provocative. That is, why do passive houses have to be more expensive?
Mm.
They don't. We have examples now. We have examples in Europe, but also in America right now, of passive houses in affordable housing, in social housing complex. Yeah, which are not more expensive than the ordinary build. Yeah, so well, I don't say that this is always the case, and especially mostly not if you do it the first time. Yeah, but but there is no reason why it has to be so expensive. Yeah, that's another part of it. That's also one of the goals we have. And how do we achieve that? Well, we are in a market economy. What you need is some competition. That's how it works. Yeah, you need some competition. There's not only one producer. It's not only one way to do it. There are many ways to do it. Yeah,
Well, hopefully, as time goes on, we'll start to get a little bit more competition in the market, and prices will come down.
and already now to be if you don't look for the most expensive ways to do it, it's not that much more expensive now. Yeah, and there is of course there can be some amount of extra investment cost. It's an investment because you save a lot of money. Yeah, it will be running 40 years, 50 years, 80 years, even longer on half of the operation costs, at least,
Mm-hmm.
than ordinary building. And if you calculate that back in the right way, you'll see a passive house already now. It's even less expensive. Yeah? On a
Mm.
life cycle cost approach. Now, I know people do not like to have a life cycle cost approach. Now, I'm 71 years old. I know how short a human's life cycle is. Yeah, so uh, 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 and even the very first passive house, that wasn't a cheap thing. Yeah, it was financed by the private investment there. It was in the range of 18% additional costs we had to spend.
Mm-hmm.
But it's completely paid back right now.
Yeah.
Already. Yeah, it's already more than paid back. And this is
Mm-hmm.
not counting for, now, just to give you one example. Uh, this four-family multifamily home, it was heated by a natural gas burner. And that burner central system, that was operating for uh, 34 years right now. Normally,
The same heater.
the same heater. But normally,
Wow.
these things last for 17 years or 20 years or whatever. This thing lasted for 34 years. And that was because it was reduced in the power it needed to provide. So it didn't. So
Wasn't working so hard.
and now we replace it. We replace it by a heat pump. Yeah,
Mm-hmm.
and this is one heat pump. It has the size, the smallest size available for single-family homes, but this is a 4-unit building.
For
The
four
price,
separate families.
yeah,
Mm-hmm.
for 4 families,
Mm-hmm.
one heat pump, which normally is used for just a single-family home.
Mm-hmm.
That's already, no, it's not a quarter of a cost, but it's around half of a cost. Adding in that this is now 34 years later, yeah, even from that point of view, it has been much less expensive to live in these buildings and to have them working all the time. There has been no repair anywhere on any of the um, window frames, the thermal envelope, the roof, the air tightness, and so on. This is all working like it was 34 years ago.
That's amazing.
It might be surprising, but and this is for the first prototype. This is not the standardized product of a big company. Yeah, it's not the Mercedes. Yeah, it's by built by handicraft work on site. Yeah, and it is working well. Yes, we have looked into the building physics, and that's again proving that physics works.
Mhm. Science works.
That's the main thing. Physics works, and it's sometimes a little bit strange to have all these discussions about where people think that physics doesn't work. I don't understand that. It's so clear. Yeah, physics always works.
Yeah. Yeah. I guess it's just, especially in the current climate with construction costs escalating so quickly over the last, 3, 4, 5 years since COVID, it's
Yeah.
even more difficult for people to get their heads around. But
And
I think if we can just get the message out there that, as you said, the physics works, and a house is expensive anyway, and the costs that you save in not only running costs but also the repair costs is going to outweigh what you spend at the upfront
add in
stage.
the trouble. Add in the trouble. If you have a leaky roof, what kind of trouble is that? It's not just the cost of a repair. Yeah, it's also the lack of quality of life. Yeah.
Yeah. Absolutely. So, what do you think the biggest misconceptions about air tightness and indoor air quality are that you still come across? You've mentioned in the past that a building should work like a thermos flask. Or, in Australia, we have eskies, which we put all of our barbecue meat in when we go out to have a barbecue. But these things are airtight and highly insulated, but they don't have people in them, and there's no cooking inside them. So, what's your comment about airtightness and indoor air quality and the misconceptions in passive house?
The thing with a passive house the analogy only serves to explain how one part of a building, and that's the most important part, that is the heat flow out of a building, how that can be reduced, namely by flow of heat conduction. This is where the comparison, the analogy to the thermos flask comes in. But it's not that building itself. Let's put it another way. Passive houses breathe. This is what we exactly do. In the best possible analogy of breathing of, say, a camel. The camel, it's an interesting animal. The camel has the highest known heat and moisture recovery system in its nose. These animals, they recover more than 80% of humidity. We don't do it even with the best ERVs. Yeah, this is a natural concept. Yeah, and now that's the analogy for another part. The next important part of the heat flow, that is convective flow. Yeah? So we also can reduce that convective flow. Yeah? And then there's indoor air quality, best possible indoor air quality. That's a criterion for passive house. And in all climates, this can be achieved by a breathing system. And engineers call it a fresh air ventilation system. Yeah? That's the way buildings breathe. They breathe through the ventilation system. They don't breathe through the envelope. So as we, of course, we breathe also to our skin, but that's a very small part of breathing process. It's less than 0.1% or whatever. So if you stop breathing, you have a problem. Yeah, you can't breathe only through your skin, and that's the same thing with a building. Yeah. So now this is also again it's an somehow abstract discussion, and this is why I come up with the analogy with the camel and with these things, because people want to understand what's going on here, and it's correct. We want to understand that, but again, the most important thing here is practical experience. Yeah, go to the passive house, go inside it, smell the air, talk to the occupants, and then you'll see how it's working.
Some critics say that passive house locks us into a technological mindset. Ventilation systems and heating and cooling demand and lots of technical speak, when what we really need is simplicity and adaptability. Are they right? And I guess this goes back to the passive house principles discussion as well. How can we simplify, or do we need to simplify?
It might be surprising, but passive houses are the simple solution. If you think about it, yeah.
When you understand how.
Sometimes people think things are difficult or complicated just if they are not used to it. Yeah. And but the simple solution is understand how a building works. There's no way around it. We want to understand that, and now use the fundamentals of physics to ensure it functions properly. And insulation isn't rocket science. Yeah? So now, if we reduce the power needed to run the technical system, this is exactly what we do. Yeah, then the technology is simplified. Yeah. Ordinary buildings. What is the ordinary buildings? These systems used in ordinary buildings, they are typically 20 kilowatt rocket burner powered systems that consume tons of oil annually and convert it into CO2. You can always say, happy, simple building. This is not simple. It's an interesting thing. And the concept, especially my friend Bo Adamson came up with, was to come to a simple solution. And it is a simple solution. Now, if there are some things which very often modern buildings still do not have, like a proper fresh air ventilation system. But if you look into the science of the people who are really looking into air quality, there is no doubt at all that we need that. Not to save energy, but to have better indoor air conditions in the buildings. Yeah, that is, and it's a simple way to do it. Now, if you are not used to it, if you see it for the first time, and if it's not well designed, you might think it's a complicated technology. It's not. Every washing machine is more complicated than a full ventilation system.
You know what? The settings on my washing machine are really complicated.
They are. Try to repair your washing machine. Yeah. But that might be surprising. You can actually repair your ventilation system. This is not that difficult. Yeah, you can. It's not that difficult. You can't damage too much things there. Yeah. Not like gas burner. Try to repair your gas burner. I wouldn't recommend. It's dangerous. Yeah. These things can explode. Yeah.
Yes.
There's nothing to explode in a ventilation system. Not at all. You can change the ventilators. It's the modern passive house ventilation system has a ventilator which is commonly in every in every modern PC, in every modern personal computer. It's the same for ventilators. Yeah, easy thing
The fan
to
system.
Yeah, the same.
Yeah.
It's exactly the same ventilators, and they have become much more efficient since and then we introduced the first air heat recovery system in first passive house. There was only one product all around the world available that was even near to be useful for the purpose. It was produced by a Danish factory, and it was the only one which has existed since 20 years. But it came with a ventilator using 100 watts of electricity. And that makes no sense. It's too loud and it's too high consumption. So first thing we did in our laboratory, we exchanged these ventilators to then available electronically communicated systems. These are now commonly used everywhere. So nowadays you have 8 watt, 10 watt ventilators in these systems. Simple thing to exchange. It's also not high voltage. We're running on 18 volts, 24 volts, or whatsoever. This is a simple technology.
I think it's everything's easy when you know how. So the theme of this conversation is to just
I'm not
keep
sure.
asking questions.
For example, going to the moon isn't simple, even if you have the know-how.
True. Touche.
Yeah. So there's a difference. It's completely clear. There is a difference. But we have. You can build your own heat recovery ventilation system if you take the time to do so. It's not rocket science. It's a very, and we have seen it. Some people may say, "Oh, I don't want to use electricity, to consume electricity to run the system. I want it to be working with the natural forces." And we even have some example passive houses in France where they have done that. It's possible to do. Well, they have air channels which are half a meter in diameter to even reduce the resistance of flow even more. It's possible to do, yeah. And I would say, well, but what is a 10 watt ventilator added to the system? Add another half a square meter of photovoltaics on your roof, and it's run completely by free electricity. This is just another pragmatic, it's a pragmatic part of approach to see that this is simple technology, and of course you can make it better and better and more sophisticated, and that's what the industry production is all about. And they have made a lot of progress. Yes, you can improve the control system nowadays. That's another thing. Yeah. So now every mobile phone has more calculation capacity nowadays when I had running these 10,000s of simulations in 1987. Yeah. It's all there. It's all available. It's a question to make it approachable for the ordinary person. This is what is somehow also behind the passive house idea. Yeah, to make it approachable. It's not something which is just designed by some clever engineer way away from your own property. It can be done. You can learn it if you want to. You don't need to. You can use the expertise of all the people around you, but in principle, you can do it.
We've got a couple more questions. If a builder or a homeowner can't achieve full certification, passive house certification, what should they prioritize?
Oh, use the PHPP. Use the passive house design package.
Use it anyway.
You use it anyway. Yeah.
Yeah.
To calculate the energy balance, or have somebody calculating it. Yeah, you can use Design PH, for example. It's a very easy tool, to use. Also something you learn on your own. It's not so difficult to do, and then you can optimize your construction as far as you want to go. Yeah, of course, you can do that. And there is a reason why the criteria have been chosen the way they are. Yeah? So it's worth to come as near as possible to the actual standard. This is not. It's not. But the standard is not there to create a challenge. It's there because it is the most recommendable way to go. You see, passive house is not a zero energy building. No. And we do not need zero energy because you can produce energy with your photovoltaic system. And there is a grid of electricity that is available almost everywhere on the planet. And where this is not available, you can build autonomous homes. Yes, you can. And the best way to do it is to build a passive house, do it a little bit better, and add some more photovoltaic systems. Yes, so at the end, that's it. And if you do not come to a full standard in first place, well, hard for me to think about what you should, what you can. What's the thing you need the least? Maybe
Yeah,
the
it's
thing
hard to
that
pick it apart, isn't it?
the thing that really adding some cost is the ventilation system. But I wouldn't recommend to build any new residential building nowadays without a ventilation system.
I think that's probably the first thing that people give away in Australia, this ventilation system.
See, the ventilation system is almost the only part which adds some extra cost, from what you ordinarily do. But I wouldn't recommend to build any new residential building nowadays without a ventilation system, because this is something you need for indoor air quality. It's not about energy efficiency. It's just providing healthy indoor climate. That's what a ventilation system is used for. Yeah.
Yes. Yes.
So
yes.
it's just,
and that is where we are coming to in Australia. We are coming to that point where it's not just about, we always talk about what air changes do you need to start introducing mechanical ventilation? And the response is becoming more and more, well, there is no air changes per hour there's a cutoff. There's no magical number. We need to ventilate regardless. Yeah. All right, Wolfgang, may I call you that? May I call you Wolfgang?
Of course. That's my name.
A final question. What is the one thing out of everything you have learned in your career that you want the listener to know? If you had to pick one thing.
Remember, we build and renovate for humans, not exclusively for investors. Yeah. So there is a responsibility for every designer, planner, construction engineer, and worker. And that is design the buildings to be healthy, to be comfortable, easy to use, and affordable for the occupants.
That's very good holistic advice.
And it's not difficult. And I hope we have contributed to make it less difficult. This is what it's all about.
Thank you very much, Wolfgang. It has been an honour and a pleasure to talk to you tonight. Well, this morning, where you are in I believe you're in Darmstadt, did you say?
Exactly. Yeah.
All right. Thank you very much.
Thank you. Bye.
That is all for today. Thanks so much for tuning in. There will be another episode in a fortnight, so if you would like to listen into the types of conversations that I have all the time, please subscribe on your chosen platform. Rate the show, leave a comment, whatever you like, share with your friends and family. I'd love for you to spread the word about the Building Sciology Potty. There's a link in the episode description where you can head to a landing page, and there are some show notes there with relevant links and a full transcript of the show as well, and also links to my socials. So if you're not already, I'd love for you to follow along there too, as I share lots of building science and building biology tips. Thanks again. I'll be back in 2 weeks, so until then, happy healthy building.